Hello, and thanks for using TickBoom. In this video, I'm taking a look at a proof question which says if 2 to the power of k plus 1 is prime, then prove that either k is equal to 0 or k is equal to 2 to the power of n for some n greater than or equal to 0. And another way to think about that is that k must be a power of 2. Now, this question was sent to me in a comment on another video where I was looking at a proof in relation to what are called Mersenne primes. So I'll give a link to that video, but just in case you haven't seen it, a Mersenne prime is in the format 2 to the power of n minus 1. So the idea is that for some values of n, if you take 2 to the power of n minus 1, do you get a prime number? And just as a reminder, a prime number is a number with only two factors, being the number itself and 1. Now, if you haven't seen that video, I'll give a link because it might be helpful to take a look, because the technique I used in that video for that question is the same technique I'm going to use here, being proof by contradiction. So if proof by contradiction isn't something you've seen before or that you're particularly comfortable with, maybe it might also be valuable to go and take a look at this video on Mersenne primes. Interestingly, the numbers in this format here, 2 to the power of k plus 1, they're actually called Fermat primes after Pierre de Fermat. And there's a bit of interesting history here, because Fermat originally thought that all numbers in this format would be prime. And then it wasn't until a little bit later that another mathematician, Euler, was able to then prove that no, not every number in this format will be prime. There's actually only 5 of them. And so we call numbers in this format in general Fermat numbers. And then the ones of these that are prime, we call them Fermat primes. So what I might do is, after I work through this proof, I might just show some of the examples of what are those Fermat primes, because it's quite easy to do with our calculators. I think Fermat might have had a bit more difficulty kind of proving which of these would be prime or not, because naturally he wasn't working with the kind of calculators we've got now. So I think that might be an interesting exercise. But step one, we've got to work through this proof. So what I'll do, let's take a look at each of these possibilities one at a time. So for case 1, which is the case where k is equal to 0, that's fairly easy to take a look at. We'll just substitute 0 up here and see what we get. So 2 to the power of 0 plus 1 would be equal to simply 1 plus 1, because anything to the power of 0 is 1. So that's equal to 2. And that is easy to see as being a prime number, because the only integers that divide into 2 would be 1 and 2 itself. So that's a fairly easy case to work through. So now all the hard work, all the real thinking for this question comes up with our second case, where, as I mentioned before, we're going to use the technique of contradiction. And basically the idea is to start with an assumption that is the opposite of what we want to conclude. So if we take a look at this case, if k is equal to 2 to the n, I noted that that is another way of saying k is a power of 2. So if we want to use contradiction, what we need to do is assume the opposite. So for us, that means we're going to assume that k is not a power of 2. And I think maybe where it might not be obvious what to do next is, how can I represent k in this format? How do I define k such that it's not a power of 2? Because up here we said k is equal to 2 to the n, and that's a way that we can say k is a power of 2. Now, to do the opposite, we can actually say k is equal to something times 2 to the n. So I'll just call it m, just for another letter. So m times 2 to the power of n. And I can know that this k will not be a power of 2 if m is basically odd, or specifically an odd prime factor. So we'll say where m is an odd prime factor. So the basic idea there is that all integers can be factorized into their prime factors, and if a number is not a power of 2, then it must have at least one odd prime factor. So let's define that odd prime factor to be m, and so that's the way that we can say that we're going to assume k is not a power of 2. And from here we can now, I guess, see what mathematical techniques let us, I guess, start from this 2 to the k plus 1 and end up with some kind of contradiction. And here the contradiction will, hopefully you can see, be that if we make this assumption that k is not a power of 2, then this 2 to the k plus 1 won't be prime. Or in other words, we can find another factor that is not 2 to the k plus 1 or 1. In other words, it's not 1 or the number itself, there's some other factor. And if we can show that when this assumption is made, then we can then conclude that the reverse must be true, that if this is going to be prime, then it must be the case that k is a power of 2. So that's the basic logic. I think where we can start here, and again, admittedly, this is not going to be an obvious thing that would probably jump out at you. This is an example of a question where really just familiarity and practice is what's key. With many proofs, actually, it's really just a matter of exposing yourself to as many different kinds of techniques so that when you come across something new, you've got a deep toolkit to draw on. So hopefully the technique I'm about to show you, or the result I'm about to use, is something that you can kind of park away in your toolkit and maybe make use of it in other contexts. So what I might do is just, I'll note, as a little side note here, that for any odd number m, and this is going to be relevant because we're kind of dealing with m being an odd number, it's possible to say that x to the power of m, so some number to the power of this odd number plus 1, that can be written as x plus 1 times 1 minus x plus x squared minus x cubed plus, and so on, up to x to the m minus 1. And I might just pause for a moment to kind of help reflect on why this particular result might help us. And then I'll actually prove it, because it's probably worth actually fleshing out why this is true, because if you can prove it, then even if you don't necessarily remember it off by heart, you can just remember that there is some result like this, and perhaps remember the technique to derive it. But the basic idea is that if we have an odd number m, x to the power of m plus 1 will have a factor being x plus 1, and that's going to potentially help us, because as I mentioned, if we want to show something's not prime, we want to show it's got a factor. And so really what we're saying is that this result kind of says, if we've got an odd number m, then x to the m plus 1 has x plus 1 as a factor. And that's really going to be the essence of this proof. So what I might do is I might just do a little side proof. So this proof isn't technically necessary to answer this question. It is possible that you could perhaps take it as given, this result. But just for the benefit of anyone who may not be familiar with this, I'll show the little proof. And it uses geometric progression. So if we consider a geometric progression with ingredients of its first term, a, being 1, and then the common ratio being negative x, and we'll say that there's m terms in this GP, then basically the way we can write that GP, it would be, the first term would be 1, the next term would be 1 times negative x, which would be minus x, the next term would be negative x times negative x, which would be plus x squared, and then we get minus x cubed, and so on. And then we'd end up with the final term being minus 1 to the power of basically whatever term it is minus 1. So this is the second term, it's the power of 1. The third term's to the power of 2. The fourth term's to the power of 3. The nth term will be to the power of m minus 1. X to the m minus 1. So that's our sequence, and notice how similar that is to this part here of our result. And that we can then kind of use our knowledge of geometric progressions and how you can add them up. So here the result would be a times r to the n minus 1 on r minus 1. That's the generic result for how you sum a geometric progression. So if we just substitute our inputs, we'll get a is 1 times r is negative x to the m, sorry, because there's m terms in this GP. So that's negative x to the m minus 1 over negative x minus 1. So if I just clean that up a little, this I could think of as the negative x to the m could be written as negative 1 to the m times x to the m minus 1 over negative x minus 1. And what's going to be helpful for us here is to think about basically this term here, this negative 1 to the m minus 1 and this negative 1 to the m. What are they? What can we know about those two elements if we're dealing with m being odd? And so we can say if m is odd, then first of all, if we start with the negative 1 to the m, negative 1 to the power of an odd number, so if we think of 1, 3, 5, and so on, we're always going to end up with just negative 1. Negative 1 to the power of an odd number will just be negative 1. And if we then think, well, what would negative 1 to the m minus 1 be? Well, if m is odd, then 1 away from m, m minus 1 would be even, and we'd get numbers like 2, 4, 6, 8, and so on. And so this negative would always be cancelling out to become a positive 1. So these two results we can insert into our geometric progression and the result for the sum, and see how we can then simplify. And I might have to turn over at this point, so I'll just rewrite the GP. So we got 1 minus x plus x squared minus x cubed, and so on. And then now, instead of writing negative 1 to the m minus 1, I can just replace that with 1. So here it'll just become plus x to the m minus 1. So plus x to the m minus 1. And what's that going to be equal to? Well, we'll have our negative 1 to the m, which we've just concluded is negative 1. So this would become negative x to the m minus 1. Negative x to the m minus 1. And then in the denominator, we had minus x minus 1. So minus x minus 1. And there's probably one more step we can do. We can just bring the negatives out. So negative x to the m plus 1 divided by negative x plus 1. These negatives cancel. And now the final step is I can bring this x plus 1 up. And so we can conclude that x to the m plus 1 is equal to x plus 1 times 1 minus x plus x squared minus x cubed, and so on, all the way up to x to the m minus 1. And that is the result that we're going to rely on. So that's a little side proof there of this result. So now, having convinced ourselves that this is something we can rely on, now we can go through the process of doing it. So what we can say is that if we're going to define k as being equal to m times 2 to the power of n, that's the assumption we've made to kind of make sure that we're saying k is not a power of 2, then what we can say is that 2 to the power of k plus 1, well, we can write that, we can just replace, instead of having k, we'll put m times 2 to the n. So it will be 2 to the power of m times 2 to the n plus 1. And just using basic rules of exponents, I could write that as 2 to the power of 2 to the n to the power of m plus 1. And now, hopefully, you can see that this is something to the power of m plus 1. And we just concluded or showed that something, x to the power of m plus 1, has a factor, x plus 1. So, therefore, we can conclude that this 2 to the k plus 1, where k is defined in this way, has a factor of, in our case, x is 2 to the power of 2 to the n plus 1. Now, the important thing to note about this number, even if we don't know n, what we do know is it's not 1, because if n is greater than or equal to 0, which is kind of what we're dealing with, then this will not be 0, so therefore the whole thing can't be 1. And it's also not 2 to the k plus 1 itself, because here 2 to the k plus 1 had this m in here, and we've kind of had that drop off in terms of our factor. So we've now got our contradiction, because we've got a factor, which means that what we can say is if k is not a power of 2, in other words, k is defined in this way, then what we know is that 2 to the k plus 1 is not prime. So, therefore, our ultimate conclusion is if 2 to the k plus 1 is prime, then it must be the case, then k must be a power of 2. Or in other words, k must be defined in this format. K is equal to 2 to the power of n. 2 to the power of n for some n greater than or equal to 0. Boom! So there you have it. That's the proof of this result that we were asked to prove, that the student who sent this question through, that's the key of what they were asking for help with. But as I mentioned at the beginning, there's a lot of very interesting history around this, and what I might do now is I might just get my calculator, and with the benefit of a calculator like this, we can actually do what Fermat couldn't back in his day, which is see, well, which of these are primes, because we can just now loop through all our values of n and see whether we get prime numbers. So I might just turn over and come back to where we are and kind of just draw a line under this, because we're kind of now going beyond the question. I mean, if all you wanted was the proof, you could probably pause now, but if you're interested in this kind of history of Fermat numbers versus the Fermat primes, well, what we can do is very easy for us to now take a look. So let's just start. We'll start with n is equal to 0. So what would we get then? Well, we get k is equal to 2 to the power of n, or in other words, 2 to the power of 0. And that is equal to 1, because anything to the power of 0 is 1. So what that would mean is that our 2 to the k plus 1 would become 2 to the power of 1 plus 1, which would be just 2 plus 1, which is equal to 3. And 3 is a prime number. So here we have our first Fermat prime, which is a Fermat number that happens to be prime when n is equal to 0. Now, let's see if we can squeeze in n is equal to 1 here. So when n is equal to 1, k would be equal to 2 to the power of 1, which is just 2. So therefore we get 2 to the k plus 1 would be 2 to the power of 2 plus 1. And that will be equal to 2 squared is 4, so 4 plus 1 is 5. And hopefully you can see that 5 is also prime. So there is our second Fermat prime. So I'll definitely have to turn over now. Let's take a look at n is equal to 2. So when n is equal to 2, k would be 2 squared, which would be equal to 4. So therefore our Fermat number 2 to the k plus 1 is equal to 2 to the power of 4 plus 1. Now I might just use my calculator now just to make sure I don't make mistakes. 2 to the power of 4 plus 1 is 17. Now, is 17 a prime number? Now, at least on my calculator, what I can do is I can hit shift and then this kind of circle comma button, which gets us factors. So if I go shift factor of that, you see at least my calculator is really thinking about it, and it doesn't immediately give me anything, which kind of is my calculator's way of saying no factors. So if I type 17 and say give me the factors, we just get nothing. So at least with this calculator, that is a way I can say yes, I can convince myself that 17 is prime. So far for the first 3 values of n we've used, n is equal to 0, 1 and 2, they've all resulted in these Fermat primes. And perhaps you can then kind of see why Fermat might have thought, hey, maybe these are all prime, like for all the numbers I'm working with, it's all giving primes. So let's keep going. Let's take a look at n is equal to 3. So k would be equal to 2 cubed, which is 8. So therefore 2 to the k plus 1 would be 2 to the 8 plus 1, and that I definitely will need help with. 2 to the 8 plus 1 is 257. And again, let's see if there's any factors. No factors, so 257 is prime. Alright, now let's take a look at n is equal to 4. So n is equal to 4. K would be 2 to the power of 4, which is 2 to the power of 4 is 16. So therefore 2 to the k plus 1 is equal to 2 to the 16 plus 1. And what's that? 2 to the power of 16 plus 1 is 65,537. Now this would be very, I think it would be rare for anyone to be able to look at this and ask, is it prime? But again, our calculator can help us. And no, no factors, so prime. So here we are, we've now worked through how many? We've worked through 1, 2, 3, 4, 5. The first 5 of the Fermat numbers have all turned out to be Fermat primes. And you can kind of see we're starting to deal with bigger numbers, and you can probably imagine, okay, perhaps without the calculating power that we've got, perhaps it might not have just been an easy thing to keep going and look at n is equal to 5 and so on and see whether they're prime. But we can. So I'm going to go n is equal to 5, and this will be the last one I look at. So we'll go k is equal to 2 to the 5, which equals 2 to the power of 5 is 32. So therefore our 2 to the k plus 1 Fermat number would be 2 to the 32 plus 1, 2 to the power of 32 plus 1. Now that's going to be 1, 2, 3, 1, 2, 3, 1, 2. So we're going to go 4, 2, 9, 4, 9, 6, 7, 2, 9, 7. And that's a big number. So again, without a calculator, it's going to take a lot of, I guess, mental brain power to work out if this is prime. But I'm just going to use my calculator. And here we see the calculator has worked out this is not prime because 641 is a factor. And so here we have our first example where we've got a Fermat number that is not a Fermat prime. And whilst I've been able to kind of demonstrate that pretty easily with my calculator, Euler, back in the day, was able to prove, or at least disprove, Fermat's hypothesis that all of his Fermat numbers, all of these 2 to the k plus 1s, would be prime. Very easy to prove now because you can just use a calculator to find one counterexample. But Euler actually exhaustively showed that actually, apart from these first 5 primes that I've just demonstrated, none of the other Fermat numbers are prime. It's just those first 5, which I actually thought was really interesting. When I was first looking at this question, when I was first kind of pondering, well, what's this question about? How would you prove it? I kind of instinctively thought it's probably going to be contradiction, just because that's the technique I used for this very similar question of Mersenne primes. But just to play around, I just started doing the math on what do you get for all your values of n. So my first step in thinking about this was to work through this process, and then I got to 5 and then realized, oh, I got a bit more of insight as to what I'm really dealing with. Because the temptation might be to say, well, what this is saying is that if 2 to the k plus 1 is prime, then k will be equal to 2 to the power of n for all n. Whereas you need to be very careful with the language. It's only saying for some n it will be in this format. So there are many, many values of n for which 2 to the k plus 1 is not prime, as Euler demonstrated. So I mean, sometimes there's value in just kind of playing around with the question and kind of just taking the time to, you know, do a little bit of grunt work and just actually plug in some numbers and see what you're dealing with. Because that very simple step for me actually moved me beyond where Fermat was, which was, hey, they're not all going to be prime. There's at least one that's not prime. So hopefully you found that little extra exercise insightful and somewhat interesting. I think very often the history of math and the different personalities that you encounter, they can be just as interesting as the actual mechanics themselves. But hopefully, at least in terms of this proof, that you found that proof helpful, that the contradiction process made sense. If you did find that explanation helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.